Method number two is what I said was custom. So saying that if I knew at point C, I didn't do as good, so I'm going to throw a little bit more air inside there. D, I was really awesome, so I put the least amount of air inside there. The others, B as well, could have also been bad. So whatever it takes, you make this adjustment. This is your call. So now you end up at, you total that up to be the 11 seconds. And then you put that and adjust those angles appropriately. So you end up at 540 degrees. If you really knew one angle was that awful, you could theoretically put all the adjustment onto this one single angle. But keep in mind that every angle does have some sort of air inside of it. It's not perfect. So in reality, you're going to have a correction for every traverse station you have for each angle you have. And keep in mind, these are the same angles I showed you on the previous chart. These are your measured interior angles that we're trying to do to create the adjusted angle, but in reality, instead, if you don't want to call it adjusted, let's just call it balanced. Would probably be a better word right there. So these are your balanced angles. So that's step number one. Number two is we want to create our preliminary azimuths and bearings. And the reason we call it preliminary is because, remember, we're making a full adjustment here. We balance the angles, and in the end, there's going to be a slight adjustment inside there. So to make that adjustment, we need to first figure out where, what it is. But to do so, you need preliminary azimuths. And then in the end, you're going to see that we'll get new ones. So here is your traverse again. A, B, C, D, E, back to A. So we need to calculate the preliminary azimuths based upon the balanced angles. All right, we just balanced them. So here's where the measured interior angles were. These are now the balance. And this is the balance based upon an average correction for each. Right, everyone had a 2 second, 2 second, a 3, a 2, and a 2 second correction. Allows me to get back down to 540 degrees exact. All right, so if you recall, throughout lately we talked about how to do station sketches. This is exactly what it is. This is how you're going to be able to calculate these preliminary azimuths based upon these interior angles. So if I gave you that the azimuth of A to W is 234 degrees, 17 minutes, 18 seconds, and I also told you that you had an angle right of 151 degrees, 52 minutes, 24 seconds as you look to E. So that goes all the way over. So if I told you that, now you can do exactly what we've been talking about before, these station sketches. You can now start figuring out what exactly these azimuths are. So given one azimuth, and now I have all my interior angles. Here's that first one I just gave you, from WA to E. And now you can start calculating exactly what these azimuths are. So now these are what we call our preliminary azimuths. So you would then, at each station at A, B, C, D, and E, you would calculate these azimuths individually. Of course, you can use software and you can use other things and other methods to do so. But as we've been doing it by hand, that's exactly what's happening here. All right, so now that we've done that, we want to now calculate our departures and our latitudes. You're kind of curious, well, why we want to do that? Well, this is the method of how we're going to be able to make this adjustment in the end. So if you recall our departures and our latitudes, departure was L. L is obviously the length. Length times the sine of alpha. Alpha, so we talked about departure is east-west, latitude is north-south. And these are actual coordinates. These are changing in numbers in eastings and changing north and number in northings. Or change in x and change in y, whatever it may be. We call them cardinal direction because it's going right along parallel to the axes, parallel to the x-axis or parallel to the y-axis. So you have L, that's the length from A to B in this instance as you see here. It's the length from any 2 points that you're trying to do. Okay, alpha, now alpha is the azimuth. You see where alpha is measured from right here? Alpha is your azimuth. Make sure you always keep in mind, if you always use the azimuth, you're never going to have a problem to be able to know what was actually calculated. So in this instance, I'm always going to use azimuths. It's easier, and through the sine and cosine and your tangent functions, those trig functions based on an azimuth knows the direction you're going, so there isn't ever any doubt or ambiguity as to what really it is you're looking for. So we will use azimuths. So take a look here. What we're trying to figure out now I already gave you the chart of what those departures and latitudes are. And let me show you now exactly what it is we did. So the departure, if I'm going from A to B, you can see that my departure, again in cardinal directions, meaning parallel to the x-axis or parallel to the y-axis. So departures parallel to the x. So departure, to get from A to B, I go 517.45 feet to the east, and using this equation, that's how I'm going to be able to calculate that. Latitude, then I get 388.82 feet. What's important that you recognize is the sign of the number. Is it a positive or a negative number? Well, we went from A to B, so obviously we're going further down. We're going at a negative y value to be able to get there. So make sure you pay attention to what the signs are. If we continue on, I now go from B to C. So using that same thing based upon the azimuths, I'm using these equations back here. I can calculate the departures and latitudes. So calculate the departure and latitude down to C. That's what those are. Do the same thing. Let's go up to D now. Calculate those. Now I'm going to go from D to E. Again, same equations we're using, and we're using the azimuths. Remember the azimuth from D to E, that exact azimuth. I'm using 284 degrees, 35 minutes, 20 seconds to be able to compute this. That's why we calculate those preliminary azimuths. Now in the end, this is where we're going to figure out, what's really going on with this traverse and how well we did. Because in this instance, we're dealing with the actual lengths. We didn't just take balanced angles. No, we're taking the azimuths as well, the distances, to be able to calculate where we are. So finally at E, getting back from E to A, those are our departures and our latitudes. Now you can see, so take all that into account right there. Now, theoretically, if I began at A, I should end at A. So what that means is, if I went so far to the east, I should eventually make it so far back to the west. Or if I went so far in a positive x, I should make it so far back in a negative x direction to end exactly where A is. Same thing in my northings, or same thing along the y. Every negative y, I should have an equal and opposite in the end of a positive y, so I end up exactly at A. Now you can see here, if I sum up my departures and sum up my latitudes, I don't end up perfect. They should be zeros. That would mean I did everything awesome and perfect, but what that tells me is that I wasn't perfect. There was a little bit of error inside there. So what it means is I ended, look at the value of the number, whether it's a positive or negative. You see here that both numbers are positive, so that means I ended up to the east or along a positive direction in the x away from A, and also a positive direction in y away from A. Okay, so now that we know where we ended up, we didn't end up at A, but we ended up somewhere really close. Now we can calculate how good was this traverse. So this is what we then do by our linear misclosure and our relative precision. So again, here's the same information I just showed you before. Linear misclosure, we talked about, where it is we actually ended. It's the hypotenuse. We want that linear. We want the actual distance that you misclosed. We're not talking just in coordinate values of so far to the east and so far to the north. We're talking the actual distance away that you've misclosed. So if you remember what I told you before, we ended up too far to the east and too far to the north. And so that's what the red dot represents right there. And what we are looking for now is our linear misclosure. That's the yellow line, the exact line. So it's the hypotenuse. It's the hypotenuse then of your closing errors. So to calculate that distance, it's just a distance formula. You got to come up with that. So you take the linear misclosure, it's just the square root of the departure squared plus the latitude square. It gives you the value. So overall, our linear misclosure was 0.081. So 0.08 of a foot. Really, that's awesome. That's not bad for those distances you just went out. So that is what your linear misclosure is. Relative precision. We've talked about this before in previous lectures to kind of giving you an idea of how well we do on certain distance measurements or anything overall. This is not how well you did on your on your distance. It should have ended up at A, but we didn't. Based upon that 0.08 of a foot that we misclosed, Relative precision then is taking that linear misclosure and you divide it by the total traverse length that you went. So remember, we're not dealing in angles here, we're dealing in distances now. So you take that total of the 2466, you put a ratio to that, and you end up about 1 in 30,000. So your relative precision is about 1 in 30,000, meaning every 1 foot of error per every 30,000 feet that you survey. That seems pretty good. The better it would be 1 in 300,000, 1 in 3 million, 1 in 30 million, whatever it is. But this tells you exactly how, this is your linear misclosure and then also your relative precision. So that is your calculator. That tells you now how well your survey just was.